No, you won't have to copy down the questions, just answer them. And I'll send out information about the exam this weekend about how everything is going to go down. So everything should be clarified, by Sunday or so. So last time I introduced this idea of how you get the force from the potential energy function for that associated to that force. So now that we have this formula, given if you know what U is, the potential energy function, you can get the force. Why don't we just check it and make sure that it works on some of the ones that we're already aware of? So let's test it on, for example, gravity. So I'm going to set up a coordinate system, as you usually have to if you want to talk about forces and potentials. Just going to use that coordinate system. Then in that coordinate system, the potential energy function is just mgy, right? And I could add a plus u naught, and I'll get to that in a minute. So from the formula above, the force is negative partial derivative with respect to x of mgy in the I hat direction, minus partial derivative with respect to y of mgy in the j hat direction, minus partial derivative with respect to z of mgy in the k hat direction. Now, remember what a partial derivative means. It means you treat every other variable as a constant except the variable that you're taking the derivative with respect to. So this first term, there are no x's there. So that means we treat everything else as if it's a constant. So that's just 0. That term is 0. This term, well, m and g are both constant, but y is just y. So we take the derivative with respect to y, and we get minus mg in the j hat direction. And then this term is also 0 because there's no z's. So we treat the m, the g, and the y all as constants. And so that checks out. The force in the gravitational force is negative mg, or it's mg in the negative j direction. Just a quick note. We could have equally well used a different potential energy function. We could have used u sub g of x, y, and z is mgy plus u naught, where u naught is just some arbitrary constant. And the reason for that is that the partial derivatives of u naught are all 0. And that's just because u naught's a constant. So the point is to go from potential energy to force, you end up having to take derivatives. And so, of course, it's okay to add constants because derivatives of constants is 0. And if at the end of the day, all we care about is the difference in potential energies and derivatives of potential energies, any constants just don't affect your end result at all. All right, let's look at another example. Let's look at the spring. So let's suppose a spring is displaced. Not a string, sorry, string theory and all that. A spring is displaced in the x direction. So the picture here is something like you have a wall, maybe that's x equals 0, and then you have your spring, and then you have your equilibrium distance x0. And maybe there's a mass on the end. And so then this position might be x, right? So then the elastic potential energy, we know that that's given by 1/2 times k times the displacement from equilibrium squared. So the displacement from equilibrium is just this distance here. So that's x minus x naught. So this is x minus x naught squared. Okay, now let's take the derivative. So the force, sorry, let's take 3 derivatives, but it's not so hard because most of the terms are 0. So the force is negative partial derivative with respect to x of 1/2 k x minus x naught squared in the I hat direction, minus partial derivative with respect to y of 1/2 k x minus x naught squared in the j hat direction, minus partial derivative with respect to z of 1/2 k x minus x naught squared in the k hat direction. All right, so let's take some derivatives. Well, let's look at these terms, the last 2 terms first. So in the second term here, there is no y in this expression, right? So we treat everything else as a constant. K, x, and x naught are all constants in this case. So the derivative of a constant is 0. So that gives us nothing. and similarly in the z hat direction. Sorry, in the k hat direction. And then we just take the derivative of this term as we normally would. And that's not too hard to see, that you get a negative sign out front, that's still there. The squared and the 2 cancel, so we just get a negative k, and then we get x minus x naught. I should point out that well, how do I want to phrase this? No, it's fine. Yeah, so this is what you end up with for the force, and this is in the I hat direction. And that is precisely what we expect, right? That is, F is equal to negative k delta x displacement. Or sorry, k times x displacement, where x displacement is x minus x naught. So that checks out. And again, we could have added a constant here and that would have been totally fine. So great, we're able to, if given a potential energy function, we now know how to find the force. So another question that you might have, and this is a question on the homework, is how can we find out if a function, if a force is non-conservative using this technique? So why is it negative? There's a negative out front. So this sign just carried through, that's all. And the reason why that sign is there is it just comes from the definition of a force and how it relates to the derivative of the potential energy. Right, so how we do this, there's 2 steps. So integrate, the first step is integrate, or perhaps the correct statement would be anti-differentiate, but you guys probably view those 2 things as the same thing. Basically, just don't put terminal, like an integral is when you have like a and b, and antiderivative is when you don't have those. Is it just 1 if you do the chain rule? Is what just 1? Yeah. So it's because it was x minus x naught squared. So the derivative of this is 2 times x minus x naught times 1. That's all. Right, so first step is we anti-differentiate the, say, x component of the force to get a general function for the potential energy. That works for that component. So I'll explain what I mean by this once I finish writing. So we know that that if you anti-differentiate, that's like, if you take the derivative of something after this is the fundamental theorem of calculus, right? This is just true. So we know that in order to go from the potential energy function, you take the derivative. So in order to, so say you want the force in the x direction. In order to go from the potential energy function to the force in the x direction, you take the derivative with respect to x and slap a minus sign in front. So what we do is we start with the force in the x direction, and we anti-differentiate, and then you have to apply a negative sign. Because that way, so let's say we start with force in the x direction, then we anti-differentiate and stick a negative sign in front. Because if you then take the derivative of that and stick a negative sign in front, you just get the same thing back. So what we're doing is we're creating a candidate for the potential energy function. And so that will give us a potential energy function that certainly works for the x component. And then next step is check that the candidate potential energy works for the other components. And when I say works, what I mean is just take derivatives. Take partial derivatives and see that the potential energy function that you had agrees after you take partial derivatives with the other components. So let me do a quick example. So first question a question might be, is the force F equals AXY in the I hat direction conservative? So first things first, so what we can do is we can make a simplifying assumption. It's safe to say that if it is conservative, then the potential energy function, U of X, Y, and Z, is actually just U of X and Y, i.e., there's no K hat directions here, and there's no Z's in the function at all. So there's no way that taking a derivative of there's no way that any derivative of this will include any part of this, right? Basically, we can ignore the Z direction because the Z direction, both the coordinate Z and the direction K, neither of those show up in the problem. And that's just a simplifying assumption, and it's true in this case. So basically, we're going to work in the XY plane. So step one, work with the X component first. So Fx is AXY. By the way, let me back up. So this first step, it doesn't have to be the X component. You just have to, like, for example, if this was F equals AXY in the J hat direction, well, then you just kind of have to work with do everything in the Y direction and in the Y component. You can just pick whichever one you want. The point is you just have to pick one. And so the X component is the most obvious choice in all of the cases. So we're going to work with the X component first, and then we're going to take the derivative. So, sorry. So if it is true that this force is conservative, if that's true, then there is some function U such that if you take the negative partial derivative of U of X and Y, then that equals F sub X, which equals A times X times Y. So what we're trying to do is we're basically trying to construct the potential energy function that it must have if it's conservative. And if we end up getting a contradiction, then we know that no such potential energy function exists, and hence it's not conservative. So if it's conservative, then this statement is true, right? Then there's some function U that satisfies this property, that this is equal to this. That means that we can just do the integral and stick a negative sign in front. That implies that negative partial X of U of X and Y with respect to X equals negative AXY with respect to X. Now, the important part here is that we're integrating with respect to X. So anti-differentiating. So usually when you anti-differentiate, you add a constant, right? If I have like f of X dx, this will be equal to some other function of X plus C. But because there's another variable, say Y, you can just treat that variable as a constant. But then the constant that you add doesn't have to be constant with respect to Y as well. It could be a function of Y. Because the general rule is as long as when you take the derivative of both sides, that term will still drop out and you'll be left with the derivative here. So it checks out. The point is you're adding a constant with respect to the thing that you're integrating. So this is equal to negative U of X, we're missing two negatives. There we go. This is equal to, this implies that we have U of X and Y has to equal, well, what's the integral of AXY with respect to X? It's minus 1/2 AX squared Y plus some function of Y. So all I'm doing is I'm adding a constant, but that constant can be a function of a variable that we're holding constant for the sake of this integral. But importantly, it's constant with respect to X, i.e. if you change X, that function doesn't change. So here's our candidate potential energy function. So step 2 is check. Test it on the other components. And so we only have to test on the Y component or the J hat component because there's nothing's going to happen in the Z direction. If we treat y as a constant, can we factor a and y out? Yeah, yeah, you totally can. You can factor a and y out from the integral, and that's how I got this 1/2 ax squared y. And then you'll just end up with negative a times y times f of y. But that's still just another, that's just g of y, say. That's just another function of y. The point is, it's just some arbitrary function of y. It doesn't matter what it is. So we know that the y direction, the component in the y direction, yeah, you still have to add f sub y. And you can call it whatever you want, c of y, g of y, whatever. I just choose f. We know that the y direction of the force is 0. So this has to be equal to negative partial derivative with respect to y of our candidate potential energy function, negative 1/2 ax squared y plus f of y. And now we can't treat this this constant function as a constant anymore because we're taking a derivative with respect to y. So that is, we have negative 1/2 ax squared plus f prime of y. By the way, partial derivative with respect to x of some function of just x. Something just happened. Okay, that's weird. This is just the normal derivative of that function. They're the same thing. And so that's just f prime of x. And similarly with respect to y. Because if there is no dependence on the other variables, then you're already holding those variables constant, right? Okay, so then that means that we have a formula for what f prime of y has to be. That tells us that f prime of y has to equal 1/2 ax squared. But that's impossible. This is a contradiction because f prime of y only depends on y. But this formula is telling us that it depends on x as well. So that means that there is no such function. There is no function u of x and y that is a potential energy for f. So what does that mean? It means that f is not conservative. So the trick is that if you want to show something's not conservative, you first suppose that it is. Suppose it is conservative. If it is conservative, what would the potential energy function look like? And then you go through the motions. You maybe do an integral, and then you take other derivatives, and then you show that you made a wrong assumption somewhere. I don't know what the component test is. Maybe I've heard it called by a different name. But this is one of the few ways that you can explicitly check a force field is conservative. The other way is just to take the curl. But we're not going to get into that. Right, so this is, okay, good question. So the contradiction here is this statement. So f prime of y is, f prime of y, by definition, is a function only of y, right? That's what this means. If I were to write this, that would mean that it only depends on x. It does not depend on y. So the fact that I'm saying f prime of y depends on x is a self-contradiction. It means that, like, I'm saying something that doesn't depend on something depends on that same thing. That can't be true. So that means I made a faulty assumption, and the faulty assumption is that f is not conservative, i.e. this is not a true statement. There is no such function that does that. When we do the second step, are we plugging the values in terms of y? I'm not sure what you mean by that. Are you plugging the values in terms of y? All we're doing in the second step is we're just taking this candidate potential energy function and then checking that potential energy function gives us the correct values in the other components. Paula, I would recommend that you don't use the curl method, if only because it's not. It'd be hard for me to mark you as wrong if you screw up somewhere, because it's not something you're expected to have learned, but that's because you haven't been taught it. So, for example, if say it was conservative, then what we would actually that's a you know what, that's a good question. I haven't actually done one that isn't. I'll just come up with one right now. Okay, let's say that f. Another example. Let's say that f is this. It's going to be a simple example, but Sorry, it's not scrolling. There we go. All right, let's see if I can come up with one on the fly. So it's going to be a little bit obvious, but let's say it's just x squared times y in the I hat direction plus 1/3 x cubed in the j hat direction, just for example. So all right, so let's check. So step one is let's check the, so let's suppose it is conservative. Then what do? Well, we write that, say, negative partial x of u and x and y, that has to equal x squared y, right? That's the assumption that we make. And then we integrate, stick a negative sign in front of both terms with respect to x in this case, dx. And so what do we get? We get that u of xy has to be equal to the negative integral, negative 1/3 x cubed y plus some function of y, right? So now let's check. Let's take the derivative with respect to y. So negative, so fy, if f is conservative, then fy, which is equal to 1/3 x cubed, is equal to the negative partial derivative with respect to y of u of x and y, which is written above, which is equal to, oh, actually, let me, I'm gonna make this a little bit more complicated. Let's call this plus 2y up here in the j hat direction, just because. Yeah, so that doesn't change anything else we've done. That means that we have negative partial derivative with respect to y of negative 1/3 x cubed y plus f of y. And that has to equal, sorry, I do need to change this part here to correspond. Because f of y, I changed f of y, so I have to change this. This is plus 2y here. That means that we have to have, it has to be the case, well, we know how to take a derivative. This is 1/3 x cubed plus f, or I suppose minus, because there's a minus in there, minus f prime of y. And that has to equal 1/3 x cubed plus 2y. Okay, so is this possible? Well, we can simplify a little bit. We see that 2y has to be equal to negative f prime of y. Well, that's certainly allowed. In fact, if f of y is negative y squared, then it checks out. And so what our potential energy is? Our potential energy function is the function negative 1/3 x cubed y minus y squared. Don't get you the same value. The force is non-conservative. It's not that they don't get you the same value. It's that the candidate, so the potential energy function basically has a few different constraints. It has the potential energy, the derivative of the potential energy with respect to x has to be the force in the x direction. The derivative of the potential energy with respect to y has to be the force in the y direction, and so on. And so because you can go from the force to a candidate potential energy function, your candidate potential energy function has to satisfy all those constraints still. It automatically satisfies the constraint for one of them because that's how you got it to begin with. But it also has to satisfy the others. And if it can't, if it's impossible, like we had up here, then you get that it's not conservative. If it is possible, such that, i.e. 2y is equal to negative f prime of y, then it is conservative. And then in fact, you actually recover the conservative, the potential energy. This is just a way to get the potential energy. All right, I gotta change gears. So for f of y, do we have a constant after negative y squared? You could, yeah, you can add a constant, and you're always allowed to add a constant anywhere. That's totally fine. You don't have to though. Yeah, you can start from f of y and go to f of x, or f sub x, that's fine. It doesn't matter which one you do, it's just you have to pick one. All right, I have to slightly change gears here because we are short for time. So we're going to talk a little bit about equipotential surfaces. I'm just briefly going to go over what they are. There's more about this in the online textbook. So suppose that I just handed you a potential energy function that looks like this. It looks like negative a, where a is just some constant, with the right units, of course, because this has units of energy, times x squared plus y squared plus z squared, as the Brits would say. So let's think about this function a little bit. We know that x squared plus y squared plus z squared, or the square root of this anyway, is the distance from the origin to x to the point xyz, from 0, 0, 0 to xyz, right? That's just the Pythagorean theorem. And so this term here, x squared plus y squared plus z squared, is just the distance squared from the origin. So the takeaway here is that every point that is equidistant from the origin, i.e. if you have 2 points and both of them are the same distance from the origin, they will have the same value of your potential energy under this potential energy function. So what does that mean? It means that points with equal potential energy, at any 2 points with equal potential energy under this potential energy function, have to be the same distance away from the origin. And so what is the shape that is formed when you take every point that's the same distance away from the origin? It's just a sphere. So that means that given it, so that implies that given, and it has to be positive here, a positive value u naught for some particular potential energy, that this is not like the constant that shows up in the potential energy, this is just some value of potential energy, like it could be 5 joules or it could be 9 joules or whatever, then there is a sphere's worth of points with that much potential energy. So that means that you can just, i.e. That u of x, y, and z equals u naught when x, y, and z are on a particular sphere. And which sphere that is, like the sphere of what radius, depends on what the value of u naught is. Like you could solve for what the radius is pretty easily. So these surfaces, in this case, it's a sphere. So these surfaces, and a sphere is a surface, right, are called equipotential surfaces. And it should be relatively clear why. Equipotential meaning the same potential, and it's a surface on which all those points have the same potential, right? So that's not particularly surprising. So the way to think about this is think of like if you guys have like seen topographic maps that look something like, you know, you have squiggly line and then another squiggly line that tell you like the height of a mountain or something. That's kind of what these are. On a topographic map, these lines are all lines of constant height, right? And on an equipotential surface, or an equipotential surface is a surface of constant height or potential energy. And in particular, all we're doing is we're just generalizing from 2 dimensions, this is 2D, to 3 dimensions, because we now have surfaces that all have the same value. And so you can just think of it, it's kind of hard to picture because that would be the equivalent of a 4-dimensional topographic map, but that's the way to think of it. These equipotential surfaces are just like lines on a topographic map. So the question is, or you might ask, what is the force from this potential energy function? Well, we can do that relatively easily. Just take derivatives with respect to each term. I'm not going to do it in a whole lot of detail, but you end up with the force being you take the negative partial derivative of it over and over again, and you get that it's 2 times a times x I hat plus y j hat plus z k hat. That should be fairly clear. The negative sign goes away because you have to stick a negative sign in front when you take the partial derivatives. The a is just sitting there, and then you have 2x, 2y, and 2z because you're taking derivative with respect to x squared, y squared, or taking derivative of x squared, y squared, and z squared with respect to x, y, and z, respectively. But what direction does this point in? This, assuming a is positive, that's kind of important here. This force direction points directly from the origin to the point. Points from 0, 0, 0 to x, y, z. So, well, what else points perpendicular or points from the origin, or what else points in that same direction? How about vectors that are perpendicular to the sphere? In this case, the force points perpendicular to the spheres, right? These force vectors are always pointing radially outwards, and the spheres are spheres, so perpendicular to the spheres would be radially outwards. So, in fact, it's generally true that a conservative force points perpendicular to its equipotential surfaces. Now, you might realize that every surface has 2 perpendicular directions, inwards and outwards, right? And I'll cover that in a minute. So we can also learn something about the direction that this points, whether inwards or outwards. Because there's a negative sign here, let's say that you look at the potential when x, y, and z are 0, when you're at the center. Then the potential energy is just 0, right? Because x, y, and z are 0, so you just get 0 plus 0 plus 0. So you get 0. As you get further away from the origin, your potential energy decreases because you have a negative sign up front. So as the distance increases, the potential energy decreases linearly, or I suppose quadratically, actually. But regardless, the potential energy gets lower. It goes from 0 to negative numbers, increasing negative numbers. And so from the origin to some faraway point, that is the direction of decreasing potential energy, right? In general, any sphere inside of another sphere has a larger potential energy because its distance is smaller. It turns out that, again, generally, the force vector also points from greater potential to lower potential. That's also always true, just like it is here. So this explains why you may have heard of things like objects tend to the minimum of their, or go in the, like objects are forced in the direction of the minimum or of decreasing potential energy. And that's precisely this reason. The force that an object experiences always points away from higher potential energy and towards lower potential energy. And in a direction that's perpendicular to its surfaces. Right, so that's just a bit of an aside about equipotential surfaces. They're good to know what they are. You'll see them again in 9C, so I figured I'd introduce them here. Now we have to talk, wait, does PE decrease moving out? Yes, it does, because look at this function here. If you increased x, y, and z, well, squaring them certainly makes it, if you had some x, y, and z value, and then you increased all of them, then that would increase everything, except you have a negative sign in front, so it actually decreases everything. So when you get further away from the origin, your potential energy decreases. Now that's not true for every potential energy function. That's just true for this one. But there's a negative sign there because I put it there. But it is always true that forces point towards decreasing potential energy. All right. Yeah, that was just an example potential energy. Not all, it would go inwards. If A was less than 0, it would point inwards, and the force would also point inwards. And you would have increasing potential energy as you go outwards. Anyway, so I have to now move on to a topic called energy diagrams. This is also on the homework, so I need to make sure to cover it. So energy diagrams are useful. It's just another tool to help us understand systems in terms of energies. And basically, all these are they graphs of potential energy in terms of position in space. And we also include, as well as graphing the total energy. So in our graph, we include both the potential energy function and the total energy. And again, you have to, because we're talking about potential energies, you have to assume that there are no non-conservative forces. Otherwise, things change. Remember, that means that there's no change in thermal energy here. So all we're going to get is changes in potential energy and changes in kinetic energy. And from these graphs, you can actually learn quite a lot. So let's look at a simple case. So a simple case looks something like this. Maybe an object under the influence of gravity, of only gravity. So that means that the potential energy, the total potential energy function, is just the gravitational potential energy function, and that's just mgy. So we can plot this. And let's say that it has some amount of energy, call it E total. So our potential energy function looks like a straight line, right? And let's say that, so this is U sub g, and then let's say that the amount of energy that our system starts with initially, or has, well, energy is conserved here because there's no external works or anything. Let's say that E total, the total amount of energy, is this high on the graph. So what we'll do is we'll draw a dotted line from that point everywhere, because the total energy shouldn't change with position, right? Even though the potential energy might change with position, the total energy will stay the same. It'll just exchange potential energy with kinetic energy. So what do we learn from this? Well, we learn that there's a place that our object cannot go further than. We call that point y max. Oh, by the way, this is a function of height, which is y. And we might have an energy here, which is in joules, right? So why is it possible? Why might we say that it can't go past, our object can't go higher than y max? Well, consider what we're doing. If our total energy, let me zoom in. If our total energy is this high, that means that we could break up the kinetic energy and the potential energy, right? So at any given point, the potential energy is just given by the distance between the x-axis and how high that potential energy is at that place. And so everything else has to be kinetic energy, right? So the takeaway here is that when the total energy crosses the potential energy graph, at that point, it's all potential energy. And so there's no more room for kinetic energy. And when the kinetic energy is 0, the velocity is 0. And so it cannot go beyond that. Like, you couldn't consider this much potential energy because you'd have to have negative kinetic energy. And kinetic energy is always 1/2 mv squared, which is always greater than or equal to 0. So you can't have a negative kinetic energy. So what this does is it allows us to pinpoint the bounds of the position of our object, if such bounds exist. It's not that there's a maximum, well, I mean, okay, there is a maximum potential energy. The point is the total energy that we have, that's our entire energy budget. And so you're allowed to exchange kinetic energy for potential energy as much as you want, as long as the kinetic energy never becomes negative. Because just by definition, you can't have negative potential energy. Sorry, negative kinetic energy. So the maximum value of potential energy is when the kinetic energy is 0. I.e., if you were to have more than that, then in order to have the same amount of total energy, you'd have to have negative kinetic energy, which just isn't allowed. So that puts an upper bound on our potential energy. And so by looking at this graph, we can just look at the point where our total energy intersects the potential energy and get the maximum position. You could have negative potential energy. Yeah, there's negative potential energy over here. That's totally fine. And I mean, if you were at a negative y value, you would have negative potential energy, right? That would just be like you're underground or something, and that's totally allowed. By the way, a note here, something that I should make sure that you guys are aware of. Zoom out a little bit. I know, unfortunately, it is fast because we have a lot to cover and I only have 9 minutes. But if you do want to catch up again, I mean, you could look through the video again, or you could check out the online textbook, it covers the same material. Just a quick note that the slope of that potential energy function, the slope is just by definition, it's du dy, right? Right, that's what it means to have a slope. And that is just the negative of the force in the y direction. So the slope is just negative mg, right? Sorry, the slope is just mg. So the slope is the negative force in the y direction. The reason for that is because of the definition. This is defined to be the negative partial derivative with respect to y, right? So we can rearrange that, put that sign over here. It's at the end of chapter 3, I think. Yeah, it's the end of chapter 3. So maybe 3.6, 3.7. And so basically the whole point here is that the slope here is just the negative of the force, right? And that'll be important in a bit. It is the partial derivative of u in terms of y, which is the same as the regular derivative. So let's look at a more complicated example. Let's look at a spring. So a spring has a potential energy function that you guys are familiar with. Hopefully, it's 1/2 times k times x minus x naught quantity squared, right? We're going to assume everything's in the x direction and so on. So maybe we call this position x equals 0. We have our spring with our mass attached. Maybe this is x equals x naught. And then maybe here is just x. And by the way, this is x equals x naught. At that position, we expect our object to be in equilibrium. All right, so let's graph this. Well, we can just explicitly graph this function. We know it'll look like a parabola. Question is what kind of parabola does it look like? Well, it'll look like a parabola that's shifted over, and I'm going to cut it off. So this is, at this place, it's x naught. So it's a parabola, but it's shifted x naught units to the right. And the reason I'm cutting it off is just because our object can't go, like, the block can't go past the wall. So it's not physical to describe the energy over there. And let's say that let's just suppose that we have total energy here. So this function here is the spring potential energy function, and that's our total energy there. So then what can we learn about this? Well, again, at any given point, we have this much potential energy and say this much kinetic energy. So knowing that the potential energy or the kinetic energy can never go negative, that gives us a minimum value of our x position and a maximum value. If it were to go past either of those 2 points, what we would find is that you would have to have negative kinetic energy, which again isn't allowed. And so what we see here is that above, when we were talking about gravity, this basically tells you, look, if the object has that much total energy, that's the maximum height that it can go. In this case, and that makes sense, if you give something kinetic energy at some height, it'll have some total energy, and there will be a maximum height that it can go to. It can't go any higher. The x-axis here, the x-axis is always energy in joules. The y-axis in this case is x. Because we're plotting energy versus position. In this case, for a spring, what we have is a maximum and a minimum value for the position of these object or of the mass on the spring. That means if you give it a particular amount of energy, then let's say you give it this much kinetic energy and you start it at the position, at the equilibrium position. Well, that means that it's moving, but it's at equilibrium. So how far can it go before the spring pulls it back? It can go this far. It can go to the position x max until the spring has enough force to pull it back. and then it'll go back the other way, and it'll compress and compress, but it can only go to a certain point, and that certain point is x min. After that point, the spring will push it away. And so this lets you figure out where the what the bounds of motion are given some initial energy. And this is all just based off of energy conservation. Just a quick aside, the equilibrium point is at x equals x naught. That's just kind of definition. And note that the slope at x equals x naught is equal to 0, right? And that shouldn't be surprising. The equilibrium point is by definition when the spring exerts no force. It's the place where the spring is happiest being. It won't push you or pull you in either direction. And further, we can look at what happens to the forces, right? The forces, they always point towards lower potential energy. So the force will point this way on the left-hand side, and it'll point this way on the right-hand side, because that is the direction of, i.e., from smaller values of x will point towards x naught, towards equilibrium. The way you can see that is just by looking at the force. So the force in the x direction is negative of the slope in the x direction. So if the slope is downwards, right, then that means that the force is positive. This implies that if du dx is less than 0, that means that the force is greater than 0. And if the force is greater than 0, that means it's pointing to the right. Similarly, if du dx is greater than 0, like over here, that implies that the force in the x direction is negative, which means it points to the left. So the whole point is that you can figure out what direction forces are in, such as just by looking at the slopes of these graphs. You can figure out things like what are the maximum and minimum values. You can figure out if it has this much potential energy, how much kinetic energy does it have, a whole bunch of things just from these graphs. So I'll just do a quick practice example, and then we'll have to work with you again on Monday. That was weird. Yeah, I have no idea what that was. Quick practice. So let's just say I give you a potential energy diagram. I give you a potential energy diagram that looks like this, right? So, one more point is that if it's true that the forces point towards equilibrium like they do here, if the forces point towards equilibrium, then we call that then it is a stable equilibrium, i.e. the object will tend to go back to that point. If they point away from the equilibrium, then it's an unstable. And if they point, if one points towards, and if one side points towards and one side points away, then it's a critical equilibrium. So let's just do this example really, really fast, lightning speed. So we have an equilibrium here because the slope is 0, and we have an equilibrium here because the slope is 0. So let's look at the slopes on either side of these equilibria. Here, and we have another equilibrium here because the slope is 0, right? So over here at this point, the force, the slope is negative here. So that means that the force is to the right, and the slope over here is positive, so the force is to the left. So this is a stable equilibrium. For this point, well, the force over here, that's positive, so it points to the left. Force over here is negative, so it points to the right. So this is an unstable equilibrium. And then we can do the same thing again here. We have a force that way and a force that way, so this is a stable equilibrium. You'll find that minima are always stable, maxima are always unstable. Further, if I told you that the amount of energy that this system had, inflection points, they don't really tell you much about whether the equilibrium is stable or not. Let's say that we had this much total energy. Well, how would we, and let's say that we initially start at this position. Well, where could our particle possibly go? I'll explain that in just a second. I know we're running over, but I need to make sure I get to this. Tenjo, you're bleeding through. I'm gonna mute him. So if this is our initial x position, then we could figure out what our maxima and minimum positions are. They're just where they intersect with the potential energy. Note that it's not these values because there's no way for our object to get over that hump. Because in order to get over that hump, you would have to have negative kinetic energy, i.e. the kinetic energy, you would have this much potential energy, and you'd have to have a negative amount of kinetic energy, i.e. your potential energy would be higher than your total energy, which is not allowed. It's not possible. And so this object would be stuck over here, stuck in this range, and it wouldn't be able to cross to the other side, even though if it could make it to the other side, it would get there. The kinetic energy is max when potential energy is minimum. So in this case, the potential energy goes below 0, so you could have the kinetic energy be all of this if the particle is at this stable equilibrium. Right, so the question was, what does stable and unstable entail? The whole point, yeah, I know it's past 2 o'clock. You guys can leave. I just have to finish this because it's important and it's for the homework. Stable versus unstable equilibrium. If it's a stable equilibrium, then the object will be pulled back towards there. Think a spring. A spring always pulls you back towards its equilibrium. An unstable equilibrium would be like me balancing my pen on my hand. Like, it will stay there, but if you just give it a little nudge, it'll fall away. So an unstable equilibrium will push you away from that equilibrium point. The y-axis is the y-axis isn't the total energy, it's just the energy. And what energy it is might be potential energy. If you're looking at the graph, total energy would be this horizontal line here. X-axis is just x. It's just position. X-axis is always position. The y-axis is always energy. All right. I'm sorry I went over, and I'm sorry that I have to run like I do, but I have a meeting like now, so I do got